In the city of Copenhagen, where the narrow streets met the sea, and the old traditions of Denmark blended with the emerging spirit of modern Europe, a child was born in the year 1885 whose name would one day echo through the history of science. This child was Niels Henrik David Bohr, and though no one could have predicted it at the time, his birth marked the arrival of a thinker who would forever reshape our view of the atom and the very nature of reality. To understand the roots of his genius, it is important to look back at the world into which he was born and the family that nurtured his mind. Copenhagen at the end of the 19th century was a city of transition, one foot in the past and the other reaching toward the future. It was a place of cobbled streets, gas lamps, and horse-drawn carriages, but it was also a city buzzing with new ideas. Science and industry were beginning to change the landscape of Europe, and Denmark was no exception. This was the environment that would form the backdrop of Bohr's early years, an environment where curiosity and intellect were valued, and where families like the Bohrs encouraged exploration of knowledge as much as the pursuit of daily life. Bohr's father, Christian Bohr, was already a respected figure in his own right, a physiologist who studied the mysteries of the human body. Christian's work on respiration and the way blood carried oxygen had brought him recognition in scientific circles, and he was deeply engaged in questions of how life functioned on the smallest levels. To grow up in a household where science was part of daily conversation meant that young Niels was never far from discussions about discovery, investigation, and the mysteries of nature. His mother, Ellen Adler Bohr, came from a prominent Jewish family known for its cultural refinement and strong tradition of intellectual life. From her, Bohr inherited not only a sharp mind but also a sense of balance, calm, and an appreciation for the arts and human values. The combination of scientific rigor from his father and cultural depth from his mother created an environment where curiosity could flourish in harmony with sensitivity to human experience. The household was one of warmth, but also of seriousness. The children were expected to work hard, to think critically, and to contribute meaningfully to conversations around the dinner table. Niels was not the only remarkable child in the family. His younger brother, Harald Bohr, would become a mathematician of distinction, known not only for his contributions to analysis, but also for being a gifted footballer who represented Denmark in the Olympics. The Bohr household was thus a place where brilliance seemed to come naturally, and where excellence was nurtured from an early age. Growing up alongside Harald meant that Niels was constantly challenged and inspired. While the brothers shared a deep affection, they also pushed each other intellectually, sharpening their minds in debates and discussions that spanned mathematics, philosophy, and the sciences. From an early age, Niels showed signs of an unusually inquisitive mind. He was not content merely to accept answers, but wanted to know the reasons behind them. He had the kind of curiosity that reached beyond textbooks and into the deeper fabric of nature. It is said that as a boy, he would often spend long hours tinkering, experimenting, and asking questions that seemed far too advanced for his age. What might seem trivial to others became, for him, the starting point of wonder. The ticking of a clock, the rippling of water, or the play of light across a glass surface, all of these phenomena were invitations to explore deeper truths. In the Copenhagen of his childhood, he could see both the steady traditions of his nation and the rapid transformations brought about by science and technology. This dual vision, of continuity and change, would later become part of his approach to physics, where he sought to honor the achievements of the past while daring to propose radical new ideas. As he grew older, the city itself became a kind of classroom. Copenhagen was home to the University of Copenhagen, a center of learning with a long tradition of scholarship. The presence of such an institution gave the young Bohr an example of what intellectual life could be. He dreamed of one day joining the ranks of those who sought answers to the great questions of existence. His father's position in the academic world provided him access to scholars, scientists, and thinkers who frequented their home. Dinner conversations often turned to the latest scientific findings, philosophical debates, or the challenges facing education and research in Denmark. These discussions left a deep impression on young Niels, showing him that science was not a distant activity carried out by remote figures, but a living, breathing pursuit, driven by human curiosity and creativity. The time of Bohr's birth was also significant in the larger context of scientific development. The late 19th century was an era of both triumph and uncertainty in physics. Newton's laws had reigned supreme for centuries, and classical mechanics appeared to explain most of the observable world. Yet, cracks were beginning to show. Phenomena such as the behavior of light, the emission of energy from heated objects, and the puzzling discoveries about the atom were hinting that something was missing from the classical picture. The seeds of the quantum revolution had already been planted, though no one yet knew how far they would grow. Into this world of both confidence and questioning came Niels Bohr, a child who would one day provide answers to puzzles that baffled even the greatest minds of his time. The first years of his life unfolded quietly, as childhood often does, but the foundation of his future was being laid in subtle ways. His father's example of scientific rigor, his mother's influence of cultural depth, the intellectual companionship of his siblings, and the vibrant atmosphere of Copenhagen all combined to shape the mind that would one day propose the quantum atom. From the very beginning, Bohr's life was steeped in the values of learning, curiosity, and dedication. When he entered school, his teachers quickly recognized that Niels was no ordinary student. He was diligent, but more importantly, he was thoughtful. He did not merely memorize facts, but wanted to understand principles. His natural patience allowed him to grapple with difficult problems for long periods without discouragement. His teachers often noted his calm demeanor, his ability to listen carefully, and his quiet but determined pursuit of knowledge. He was not flamboyant or boastful, but steady, deliberate, and deeply engaged with the material before him. In these early years, the character of the man he would become was already visible. In many ways, his childhood offers an image of harmony between environment and individual. Copenhagen, with its mixture of tradition and modernity, gave him a balanced perspective. His family, blending science, culture, and a spirit of inquiry, gave him the tools to think deeply and broadly. And his natural temperament, calm yet driven, made him well suited to the long and often difficult path of scientific research. To say that Niels Bohr was destined for greatness may be too simplistic, but it is clear that from the beginning, his life was marked by an unusual alignment of circumstance and character. Part A of this story, focusing on his birth, family, and the intellectual climate of his childhood, reveals the roots of the man who would later stand at the forefront of quantum theory. His journey began not in laboratories or lecture halls, but in the simple yet profound experiences of a child growing up in Copenhagen, listening to the conversations of scholars, debating with his brother, and wondering at the mysteries of nature. Every great scientist begins somewhere, and for Bohr, the starting point was the unique and fertile ground of his family home and his city. From this ground his mind grew, nourished by ideas, challenged by questions, and prepared to one day confront the mysteries of the atom. As Niels Bohr advanced into adolescence, the world around him was changing at a pace that mirrored the growing complexity of his own thoughts. Copenhagen was modernizing, new industries were emerging, and the power of science to transform society was becoming increasingly clear. For young Bohr, these shifts were not distant events but part of the atmosphere that shaped his imagination. Each invention he heard about, each discovery that was discussed in his father's circles, expanded his sense of what was possible. Science, in his view, was not merely a matter of facts but a living force that shaped the destiny of nations and individuals alike. It was a calling, one that he felt increasingly drawn to answer. School life deepened this sense of direction. While many of his classmates treated their lessons as obligations, Bohr approached them as opportunities. Mathematics and physics, in particular, captivated his mind. Numbers were not lifeless to him, they were tools that could reveal the hidden structure of nature. Equations were not merely problems to be solved but windows into reality. He developed a reputation for persistence, often working on a single problem long after others had given up. His patience was not stubbornness, but a quiet confidence that answers could be found if one searched with enough care. This trait would later define his scientific career, where breakthroughs came not through flashes of sudden inspiration alone, but through years of deliberate, thoughtful struggle. Family life continued to play a central role. The Bohr household remained a place of intellectual excitement. His father's colleagues often visited, bringing with them the latest scientific debates and questions. These conversations exposed Niels to ideas far beyond the ordinary curriculum of his school. He heard discussions about physiology, chemistry, and the deeper mysteries of physics. Though he was still only a boy, these exchanges gave him a sense of belonging to a wider community of inquiry. His mother's influence balanced this immersion in science with an appreciation for the humanities. She ensured that her children were not only scientifically literate but also culturally aware, exposed to music, literature, and philosophy. This breadth of experience nurtured in Bohr an ability to think beyond the narrow confines of any single discipline, allowing him to develop a style of thought that was both analytical and holistic. The bond with his brother Harold grew stronger as they both advanced in their studies. While Harold's gift was mathematics, his interest in rigorous abstraction complemented Niels's more physical and experimental inclinations. The brothers often debated and exchanged ideas, sharpening each other's reasoning. These early interactions prepared Niels for the collaborative style of science that would later become his hallmark. He would always believe that knowledge grows best through dialogue, through the exchange of ideas between individuals who challenge and inspire each other. This belief, born in his childhood conversations with Harold, would eventually shape the way he built his institute in Copenhagen, making it a center of international cooperation. By the time he entered the University of Copenhagen, Bohr was already recognized as an extraordinary student. The university was a natural choice for him, both because of its proximity to his family and because it was the intellectual heart of Denmark. There, he plunged into the study of physics, finding himself fascinated not only by the established laws of Newton and Maxwell, but also by the emerging puzzles that seemed to defy classical explanation. One of his earliest research projects, inspired by his father's physiological work, dealt with the behavior of surface tension in fluids. It was a subject that lay at the border of physics and biology, reflecting the interdisciplinary environment of his upbringing. Bohr approached the problem with meticulous care, designing experiments that required extraordinary precision. His ability to construct and carry out these delicate experiments impressed his professors, revealing a practical ingenuity that complemented his theoretical insight. The young Bohr was not a flamboyant student. He was quiet, almost shy in demeanor, but when engaged in discussion, his depth of thought became clear. He preferred to listen carefully before speaking, and when he did speak, his words carried weight. This manner of communication, patient and reflective, became characteristic of his entire life. He did not seek to dominate conversations but to deepen them, guiding others toward clearer understanding. It was a quality that made him not only a great scientist but also a great mentor. The period of his university studies coincided with some of the most exciting and unsettling developments in physics. The discovery of the electron by J.J. Thomson, the revelations of radioactivity by Marie and Pierre Curie, and the groundbreaking work of Max Planck and Albert Einstein on energy and light were beginning to shake the foundations of classical physics. For students like Bohr, these discoveries were thrilling but also disorienting. The neat, predictable world of Newtonian mechanics seemed increasingly inadequate. Something new was needed, though no one yet knew what form it would take. Bohr absorbed these developments with keen interest, sensing that he was living at the dawn of a new era in science. His birth in 1885 now seemed more than a mere accident of history. It placed him in the perfect generation to inherit the challenges of classical physics and to contribute to their resolution. Older scientists, bound by their long commitment to classical theories, often struggled to accept the radical implications of quantum ideas. Younger students like Bohr, less constrained by tradition, were more open to reimagining the nature of reality. In this way, his timing was fortunate. He was young enough to embrace the new, yet educated enough to respect and understand the old. This balance, rooted in his upbringing, would become the key to his success. The intellectual climate of Copenhagen also contributed to his development. Denmark was not the largest or most powerful nation in Europe, but its traditions of scholarship were strong. The University of Copenhagen, while modest compared to the great institutions of Germany or Britain, had a spirit of openness and seriousness that allowed students like Bohr to thrive. Moreover, the city itself, with its blend of tradition and progress, provided a cultural richness that expanded his horizons. Copenhagen was small enough for intimacy, but large enough to expose its inhabitants to the currents of European thought. This environment nurtured Bohr's dual qualities of humility and ambition, grounding him in his national identity while opening him to international collaboration. As Bohr completed his early studies, it became increasingly clear that he was destined to move beyond Denmark, to engage with the broader scientific community. Yet his roots in Copenhagen remained central to his identity. He would always return to the city, always build his most important work there, and always consider it his intellectual home. The fact that he was born in Copenhagen in 1885 was not only a biographical detail but a shaping force in his life. It connected him to a cultural and scientific tradition that valued both rigor and humanity, both inquiry and community. The years that followed his formal education would take Bohr into the heart of the scientific revolution. He would travel, meet great physicists, and propose ideas that changed the course of history. But behind every achievement lay the foundation built in his earliest years, the influence of his father and mother, the companionship of his brother, the intellectual climate of Copenhagen, and the broader context of a world on the brink of transformation. His birth in 1885 was the starting point of a life that would intersect with some of the most profound questions humanity has ever asked. Looking back, one can see how the elements of his childhood combined almost as if by design. A family that blended science and culture, a city that balanced tradition and modernity, a historical moment when physics stood at the edge of a new paradigm. All of these came together in the person of Niels Bohr. His later achievements cannot be understood without recognizing the soil from which they grew. His birth was not simply an event, it was the opening chapter of a story that would transform science itself. Thus, when we say that Niels Bohr was born in Copenhagen in 1885, we are not merely stating a fact. We are pointing to the origin of a journey that carried humanity into the strange and beautiful world of quantum theory. From the quiet streets of Copenhagen, from the conversations of a scholarly family, from the curiosity of a thoughtful child, arose a pioneer who revealed the quantum atom and forever altered the way we see the universe. The significance of his birth lies not only in the life it began, but in the knowledge it eventually gave to the world. That knowledge, like the city of his birth, continues to stand as a bridge between the familiar and the unknown, between the seen and the unseen, between the old and the new. And so, the story of Niels Bohr's life, which began in 1885 in a family house in Copenhagen, continues to inspire. It is a reminder that greatness often begins quietly, in ordinary moments and ordinary places, but with the right mixture of environment, character, and historical timing, such beginnings can lead to extraordinary ends. His first breath in Copenhagen was the beginning of a journey that carried science into the quantum age, and that is why his birth, seemingly just another event in the flow of history, holds a significance that echoes far beyond the boundaries of time and place. In the year 1913, a new picture of the atom emerged, one that would forever change science and set humanity on a path toward understanding the invisible architecture of matter. This vision came from a young Danish physicist named Niels Bohr, who dared to suggest that the atom was not the tiny solar system imagined by earlier scientists, but something far stranger, ruled not by classical mechanics alone, but by the mysterious rules of quantization. To grasp the significance of this moment, it is essential to look at the world of physics as it stood before Bohr, and to see how his bold idea cut through confusion and pointed toward a new order. For centuries, the atom had been a subject of speculation, from the philosophies of ancient Greece to the careful experiments of chemists in the 18th and 19th centuries. By the late 19th century, John Dalton's atomic theory had established that matter was composed of indivisible units called atoms, each associated with a particular chemical element. Yet as scientists probed deeper into the nature of matter, it became clear that atoms were not indivisible after all. J.J. Thomson's discovery of the electron in 1897 revealed that atoms had internal structure. Suddenly, the atom was no longer the final building block, but a miniature world with its own components and mysteries. In the early years of the 20th century, several models were proposed to explain this structure. One of the most prominent was the plum pudding model of Thomson, in which electrons were thought to be embedded like raisins in a sphere of positive charge. This picture was soon challenged by the experiments of Ernest Rutherford and his colleagues, who bombarded thin gold foil with alpha particles and observed their scattering. The results, announced in 1911, were astonishing. Most particles passed through, but a few were deflected at sharp angles, as if they had struck something solid at the heart of the atom. From this, Rutherford concluded that atoms contained a tiny, dense nucleus carrying positive charge, with electrons somehow arranged around it. This nuclear model of the atom was a major breakthrough, but it raised more questions than it answered. How could electrons orbit a nucleus without radiating energy and spiraling inward, as classical electrodynamics demanded? Why did atoms emit light in discrete colors, forming sharp spectral lines instead of continuous bands? These puzzles haunted physicists in the years leading up to 1913. It was into this confusion that Niels Bohr stepped, bringing with him not only a deep knowledge of physics, but also a willingness to adopt radical ideas. Bohr had studied with Rutherford in Manchester, where he absorbed the latest thinking about the atom. He respected the nuclear model, but saw its limitations clearly. Classical physics predicted that an orbiting electron should continuously emit electromagnetic radiation, losing energy and collapsing into the nucleus in a fraction of a second. Yet atoms were stable, and matter persisted. Clearly, something was missing. At the same time, the German physicist Max Planck had proposed in 1900 that energy is quantized, emitted in discrete packets called quanta. Albert Einstein had extended this idea in 1905 to explain the photoelectric effect, suggesting that light itself behaved as quanta of energy, later called photons. These daring ideas challenged the smooth continuity of classical physics, hinting that nature operated in discrete steps rather than continuous flows. Bohr saw in these developments a key to the atom's mystery. He imagined that electrons did not move in arbitrary orbits, but occupied specific, quantized energy levels around the nucleus. An electron could remain in one of these levels indefinitely without radiating energy, but when it jumped from a higher level to a lower one, it would emit radiation of a definite frequency corresponding to the energy difference between the two levels. This simple but profound idea explained the stability of atoms and the origin of their spectral lines. The strange regularities of hydrogen's emission spectrum, long catalogued by spectroscopists, now found a natural explanation in Bohr's theory. The year 1913 thus became a turning point. Bohr published a trilogy of papers in the Philosophical Magazine outlining his model of the atom. These papers described electrons orbiting the nucleus in distinct shells, with transitions between them producing radiation. He introduced what became known as the Bohr frequency condition. The frequency of emitted radiation equals the difference in energies between two states, divided by Planck's constant. This connection between atomic structure and quantum theory was revolutionary. It provided a theoretical framework that not only explained existing data, but predicted new phenomena. The impact was immediate and profound. Physicists, who had struggled to make sense of atomic structure, suddenly had a model that brought coherence to the chaos. The hydrogen spectrum, once an unsolved puzzle, now appeared as a natural consequence of quantized orbits. The stability of atoms, a fundamental requirement for the existence of matter, was explained in a way that classical mechanics could never achieve. Bohr's model was not perfect. Later refinements by quantum mechanics would reveal its limitations, but it was the first step into a new world. The courage of Bohr's idea lay not only in its content, but in its method. He dared to mix classical mechanics with quantum postulates, creating a hybrid theory that made little sense in terms of existing logic, but worked astonishingly well in practice. It was a leap of imagination, guided by both intuition and evidence. Many of his contemporaries found the model puzzling, even unsatisfactory, but they could not deny its explanatory power. It was, as Rutherford himself remarked, a discovery of the greatest importance. Behind the publication of these papers was a young man only 28 years old, working in relative obscurity compared to giants like Rutherford and Einstein, yet Bohr's quiet determination and deep clarity of thought allowed him to carve out a place in the history of physics. His Copenhagen background, his training, and his temperament all converged in this moment. The model of 1913 was more than a technical achievement. It was an act of intellectual bravery, the willingness to defy established rules in order to reveal a deeper truth. For the scientific community, the Bohr model marked the beginning of a new era. It showed that the atom, once thought to be beyond the reach of theory, could be understood in terms of precise laws. It demonstrated that quantum ideas, though strange and counterintuitive, were not just abstract speculations but practical tools for explaining reality. It inspired a generation of physicists to push further, to question more deeply, and to seek a full theory of quantum mechanics that would emerge in the following decade. The world outside physics also began to take notice. The atom was not merely a subject for scientists but a symbol of modernity, a window into the unseen forces that shaped existence. Newspapers reported on the new theory, marveling at the idea that electrons moved in invisible orbits, that light itself was linked to atomic transitions, that the universe was quantized at its core. Bohr, though modest and reserved, found himself thrust into the spotlight as the man who had revealed the quantum atom. Yet Bohr himself was not satisfied. He knew his model was incomplete, a temporary bridge between classical physics and a true quantum theory. He continued to refine his ideas, to test them against experiment, and to encourage others to build upon them. The beauty of his 1913 model lay not only in its immediate success, but in the way it opened doors to further discovery. It was a seed from which the entire tree of quantum mechanics would grow. The story of the Bohr model is thus not just the tale of a scientific breakthrough, but a human story of vision, persistence, and courage. It reminds us that progress often comes not from following the rules, but from daring to break them when they no longer serve. In 1913, with the publication of his atomic model, Niels Bohr revealed a glimpse of a new world, one that would reshape science, technology, and philosophy for generations to come. The revolutionary step he took in that year was rooted in the questions that had haunted physicists for decades, and in the determination of one man to find an answer that made sense of both experiment and theory. In the quiet words of those papers, the atom ceased to be a mystery shrouded in contradiction and became a structure that could be understood, at least in part, through the strange but powerful principles of quantization. For the first time, humanity could picture the atom not as an abstract concept, but as a structured system with rules and patterns, elegant in its simplicity and profound in its implications. Bohr's model was a light in the darkness, a guide into the quantum realm that would dominate the 20th century and beyond. The introduction of the Bohr model in 1913 was not the end of the story, but the beginning of a scientific revolution whose ripples extended across physics and into every corner of modern life. Once Bohr's papers were published, they spread quickly among the leading physicists of Europe. At first, many were cautious, even skeptical. The idea that electrons could simply exist in special orbits without radiating energy seemed arbitrary, even mystical, to minds trained in the strict logic of classical physics. But then came the undeniable fact: the model worked. It explained the spectrum of hydrogen with astonishing precision, reproducing results that had been puzzling spectroscopists for decades. That success alone demanded attention. Physicists began to test the model against more complex atoms, trying to stretch its reach beyond hydrogen. While the calculations grew messy, the underlying principle proved fertile. Variations and refinements appeared almost immediately. Arnold Sommerfeld, a German physicist, extended the model to include elliptical orbits and relativistic effects, improving its accuracy for certain spectral lines. These refinements revealed that Bohr's framework could accommodate more complexity than initially imagined, even if it was still incomplete. The atom was no longer a vague mystery, but a structure whose inner workings could be mapped with equations and predictions. For Bohr himself, the years after 1913 were filled with both triumph and challenge. His reputation rose quickly, and he was invited to conferences and universities across Europe. Yet he remained deeply modest, often emphasizing the provisional nature of his work. He saw the Bohr model not as a final truth, but as a stepping stone, an approximation that captured essential features while leaving many details unresolved. This humility became one of his hallmarks. He never pretended to have solved everything, but instead encouraged the community of scientists to join in the search for deeper understanding. One of the most remarkable consequences of the Bohr model was its effect on the younger generation of physicists. It inspired them to pursue new lines of research, to think boldly, and to challenge assumptions. Among those influenced were Werner Heisenberg, Wolfgang Pauli, and Erwin Schrödinger, who would go on to develop the full machinery of quantum mechanics in the 1920s. Each of them, in their own way, built upon the foundation laid by Bohr's daring proposal. They were emboldened by the realization that nature could indeed operate according to principles that defied classical intuition. The model also forced philosophers and thinkers outside physics to confront unsettling questions. If electrons did not behave according to the continuous laws of Newton, but instead occupied quantized orbits, what did this mean for the nature of reality? Was the universe itself fundamentally discontinuous, built of indivisible steps of energy and action? Such questions resonated far beyond laboratories, challenging assumptions about causality, determinism, and the predictability of the world. Bohr's work thus became not only a scientific milestone, but also a philosophical turning point. At the same time, the limitations of the model became increasingly clear. While it explained hydrogen with elegance, it struggled with atoms containing more than one electron. Its reliance on visual orbits, electrons circling like planets around a nucleus, soon showed cracks when confronted with experimental data. The model could not easily handle the subtleties of spectra from heavier elements or the intricacies of chemical bonding. These shortcomings, however, did not diminish its importance. On the contrary, they pointed the way toward a more complete theory. The inadequacies of the Bohr model were precisely what motivated the next wave of discoveries, culminating in the formulation of quantum mechanics in the mid-1920s. Bohr himself played a central role in this transition. In Copenhagen, he established an institute for theoretical physics that quickly became a magnet for young talent. Scientists from around the world traveled there to discuss, debate, and collaborate under Bohr's guidance. The institute became a crucible for quantum theory, and the discussions that took place within its walls shaped the direction of 20th century physics. The Bohr model, though soon superseded in its details, remained the touchstone that had made this revolution possible. It is worth reflecting on how bold the leap of 1913 truly was. In science, progress often comes incrementally, through small adjustments and cautious refinements. Bohr's model, however, was a leap across a conceptual gulf. He rejected the continuity of classical orbits and embraced the quantization of energy as a fundamental principle. It was a move that defied common sense but aligned beautifully with experimental evidence. Such leaps are rare in the history of science, and they mark the turning points where whole new paradigms are born. The practical consequences of Bohr's vision grew over time. Quantum mechanics, built on the foundation he laid, would eventually underpin technologies ranging from semiconductors to lasers, from nuclear power to medical imaging. These applications were far in the future in 1913, but the seed had been planted. By daring to describe the atom in quantized terms, Bohr opened the path to the modern technological age. Every smartphone, every computer, every MRI scanner carries within it the legacy of that revolutionary step. Bohr himself remained deeply engaged in the philosophical interpretation of quantum theory. He introduced the principle of complementarity, arguing that particles like electrons could be understood in mutually exclusive ways, such as waves or particles, depending on the experimental context. This principle grew directly out of the spirit of his 1913 model, the recognition that nature cannot always be forced into classical categories, but must be approached with new conceptual tools. Complementarity became one of the central ideas in the Copenhagen interpretation of quantum mechanics, shaping debates that continue to this day. As the decades passed, the 1913 model came to be seen as both obsolete and foundational. Obsolete, because the more sophisticated mathematics of quantum mechanics replaced its simplistic orbits with probability waves and quantum states. Foundational, because it was the first to show that quantization could successfully describe atomic structure, and because it inspired the generation that brought the full theory to life. In the history of science, such models are milestones, stepping stones that may not endure in their original form but remain essential in the path of progress. Bohr himself was awarded the Nobel Prize in Physics in 1922, a recognition that his model, despite its limitations, had transformed the understanding of atomic structure. The Nobel Committee praised his investigation of the structure of atoms and of the radiation emanating from them, acknowledging the enormous impact of his 1913 work. By then, Bohr had already moved beyond the initial model, but the world of science celebrated the moment when the atom first yielded its secrets to human understanding. Looking back now, more than a century later, the Bohr model retains a special place in education and memory. Students encountering atomic physics for the first time are often introduced to the Bohr picture, electrons circling the nucleus in neat shells, jumping between orbits and emitting light. It is a simplified image, far removed from the complexities of quantum mechanics, but it serves as a bridge just as it did in 1913. It offers an accessible entry point into a world that defies ordinary intuition. For many, the first glimpse of the Bohr atom is the first step into the quantum realm. The story of the 1913 model is thus a story of vision and transformation. It tells of a young physicist who, at a time of confusion and contradiction, dared to imagine the atom in a new way. It tells of a scientific community that, though initially skeptical, came to embrace a radical idea because it worked. It tells of a moment when humanity's picture of matter shifted from classical certainty to quantum strangeness. And it tells of the enduring power of imagination to reshape the boundaries of knowledge. When we speak of the Bohr model today, we are not merely recalling a historical artifact, but honoring a turning point in the human quest to understand the universe. The year 1913 stands as a marker in that quest, the year when the atom ceased to be a puzzle of contradictions and became a structured system that could be explained, at least in part, through the strange and beautiful rules of quantum theory. Bohr's contribution was not only scientific but cultural. He changed the way we think about the unseen, the way we accept that nature may operate according to rules that defy common sense yet reveal deeper truth. The revolutionary model of 1913, with its quantized orbits and spectral predictions, may seem simple now, but in its time it was nothing less than a doorway into a new reality. Niels Bohr, through his courage and insight, opened that door, and humanity has never looked at the atom the same way since. The heart of Niels Bohr's revolutionary model lay in a single, audacious idea. Electrons did not move freely around the nucleus as planets around the sun, but instead occupied specific, quantized energy levels. This concept, which at first glance seemed almost artificial, became the cornerstone of modern atomic physics. To appreciate the significance of this idea, one must return to the early years of the 20th century, when physicists were struggling to reconcile the mysteries of atomic spectra with the principles of classical mechanics. The problem began with light itself. When elements were heated or subjected to electrical discharges, they emitted light in distinct colors. Passing this light through a prism revealed sharp spectral lines, each corresponding to a precise wavelength. For hydrogen, the simplest atom, these lines formed an elegant series that had been carefully measured and catalogued. Johann Balmer, a Swiss schoolteacher, had even discovered a mathematical formula in 1885 that described the wavelengths of hydrogen's visible lines with remarkable accuracy. Yet no one could explain why this formula worked or what deeper principle lay behind it. The puzzle of spectra was one of the most persistent mysteries of physics, a riddle that taunted scientists with its beauty and regularity. Classical physics could not account for such discreteness. According to Maxwell's theory of electromagnetism, an accelerating charge, such as an electron moving in orbit, should continuously emit radiation, producing a smooth spread of colors rather than discrete lines. Moreover, the energy loss from such radiation would cause the electron to spiral into the nucleus within a fraction of a second, rendering atoms unstable. But atoms were stable, and spectra were sharp, not continuous. Clearly, something in the classical picture was fundamentally wrong. It was here that Bohr made his daring leap. Drawing on the quantum hypothesis of Planck and the insights of Einstein, he proposed that electrons in an atom could exist only in certain discrete energy states, or levels. These levels were not arbitrary, but determined by a simple condition: the angular momentum of the electron was quantized, restricted to integer multiples of Planck's constant divided by 2r. In other words, the electron's orbit was allowed only if it satisfied this quantization rule. The result was that the atom was no longer a system of continuous possibilities, but a ladder of specific states. The implications were profound. An electron could remain indefinitely in one of these quantized orbits without radiating energy, explaining the stability of atoms. Radiation occurred only when the electron jumped from one level to another, emitting or absorbing a photon whose energy corresponded to the difference between the two states. This explained, with striking precision, the spectral lines of hydrogen. The Balmer formula, once a mysterious mathematical trick, now emerged as a natural consequence of the quantized atom. For the first time, the strange regularities of atomic spectra had a theoretical foundation. Each line represented a transition between energy levels, a fingerprint of the atom's internal structure. The hydrogen atom, once an enigma, now appeared as a system governed by clear rules, its behavior encoded in the language of quantization. Bohr's model was not just a description of orbits, but a vision of order hidden beneath apparent chaos. The notion of quantized energy levels was more than a technical innovation, it was a conceptual revolution. It forced physicists to abandon the comfortable picture of continuous motion and to accept that nature imposed restrictions at the smallest scales. Electrons could not simply roam wherever they pleased. They were confined to specific states, as if constrained by invisible rungs of a cosmic ladder. The atom was no longer a miniature solar system, but a structure defined by quantum laws. The reception of this idea was mixed. Some physicists found it elegant and convincing, while others regarded it as an arbitrary imposition. Why should angular momentum be quantized? What physical mechanism enforced such a rule? Bohr himself admitted that he could not fully explain it, but he insisted that the model's success in predicting spectra justified its validity. In science, utility often precedes full understanding, and Bohr's model was undeniably useful. Beyond hydrogen, the model faced challenges. For atoms with more than one electron, the interactions grew complex, and the simple quantization rules could not easily account for all the observed spectra. Yet the core idea of energy levels remained sound, providing the conceptual framework upon which more advanced theories would be built. Sommerfeld's refinements, introducing elliptical orbits and relativistic corrections, extended the model's reach, but it was clear that a deeper theory was needed. This would eventually come with the development of wave mechanics by Schrödinger and matrix mechanics by Heisenberg, both of which preserved the essence of Bohr's quantization while discarding the planetary orbits. For students and laypeople, however, the image of electrons circling in quantized shells proved irresistible. It offered a tangible picture of the atom, one that could be drawn, imagined, and taught. The Bohr atom became a symbol of modern physics, appearing in textbooks, illustrations, and even popular culture. The idea that electrons leaped between levels, emitting packets of light, captured the imagination of a world beginning to glimpse the quantum realm. Bohr himself was acutely aware of the philosophical implications of quantization. He recognized that the introduction of discrete energy levels challenged the very notion of continuity that had dominated Western thought since the time of the Greeks. In the quantized atom, change occurred not gradually but in jumps, sudden and irreversible. This discontinuity was alien to classical intuition, yet it was confirmed by experiment. Nature, it seemed, had a graininess at its core. This realization marked a profound shift in humanity's conception of reality. The concept of energy levels also carried practical consequences. It laid the foundation for understanding chemical behavior, since the arrangement of electrons in different shells determined how atoms combined to form molecules. The periodic table, long an empirical arrangement of elements, now acquired a theoretical basis rooted in the quantized structure of atoms. Chemistry and physics, once separate domains, were united by the idea of energy levels. The world of matter, from the simplest hydrogen atom to the complexity of life, could now be traced back to the rules of quantization. The power of the model lay in its simplicity. With a few postulates, Bohr explained stability, spectra, and the periodicity of elements. Yet beneath this simplicity lay a challenge. How could such discrete rules emerge from the underlying laws of nature? This question drove the next decade of research, leading to the birth of quantum mechanics. The quantized orbits of Bohr were replaced by quantized wave functions, but the essential idea, that electrons inhabit discrete energy states, remained. It was the enduring legacy of Bohr's insight, the bridge between classical physics and the quantum world. To imagine the atom before Bohr is to picture confusion and contradiction. To imagine it after Bohr is to see a structure of elegant order, electrons climbing and descending the rungs of quantized energy. This transformation, born of his model, was one of the great intellectual achievements of the 20th century. It gave scientists a tool to predict, explain, and explore, and it gave humanity a new vision of the invisible architecture of reality. The idea that electrons could exist only in quantized energy levels did not merely solve a technical problem in physics. It redefined how scientists thought about the very fabric of matter. With the publication of Bohr's model, the atom was no longer a chaotic jumble of charges. It became a system with a clear internal logic, governed by discrete states rather than continuous motion. This concept, simple to state but radical in implication, became a central theme not just for atomic physics, but for the broader scientific worldview of the 20th century. Once the notion of quantized energy levels was established, experimentalists began to put the model to rigorous tests. Hydrogen remained the ideal subject, since its simplicity allowed predictions to be calculated with clarity. Each spectral line observed in the laboratory was matched against Bohr's formula, and the correspondence was almost uncanny. Where earlier models had failed, this one succeeded. This immediate alignment with observation gave the scientific community confidence that Bohr was on to something profound. Still, the story was not straightforward. The more scientists looked into atoms with multiple electrons, the more they encountered complications. The energy levels in these cases were not simple circles, but were influenced by electron-electron interactions, spin, and relativistic effects. Yet, rather than undermining Bohr's central idea, these challenges demonstrated its robustness. The principle of quantization endured, even as the specific details were refined and extended. Each refinement deepened the understanding of atomic structure, while the essential insight, that electrons inhabit distinct levels, remained untouched. The impact of this concept soon rippled into chemistry. For decades, chemists had organized the elements according to the periodic table, noting patterns of reactivity and valence, without fully understanding the underlying reason. Bohr's energy levels provided the missing explanation. The arrangement of electrons in shells and subshells dictated how atoms bonded, why certain elements shared properties, and why noble gases resisted chemical combination. Suddenly, the periodic table was not just an empirical chart, but a window into the quantized architecture of matter. The boundaries between physics and chemistry blurred, as the language of quantized orbits gave coherence to both disciplines. At a philosophical level, quantized energy levels forced scientists and thinkers to confront the idea that nature is not infinitely divisible. The classical notion of continuity, inherited from centuries of tradition, was broken. Change at the atomic level was no longer gradual but sudden. An electron did not glide smoothly from one orbit to another, it leapt, releasing or absorbing energy in discrete packets. This idea, which Einstein had already hinted at in his work on the photoelectric effect, now became a central feature of atomic structure. The universe, at its foundation, was granular, punctuated by quantum jumps that defied common intuition. For Bohr, this discontinuity was not a weakness, but a signpost toward a deeper truth. He argued that scientists must adapt their concepts to nature, not force nature into preconceived frameworks. The quantized atom exemplified this principle. It seemed strange, even counterintuitive, but it aligned with experiment. And in science, coherence with observation is the ultimate test. The Bohr model's portrayal of quantized energy levels also inspired new tools for technology. As the decades passed, the idea of electrons jumping between levels became the basis for lasers, semiconductors, and other innovations. When an electron dropped from a higher state to a lower one, it released a photon of precise energy, corresponding to a well-defined wavelength of light. Harnessing this principle allowed engineers to create sources of coherent light, paving the way for laser technology. The same logic underpinned the understanding of semiconductor band structures, the foundation of modern electronics. Without the quantized levels first envisioned by Bohr, the digital age would have been inconceivable. Yet it was not only technology that benefited from this vision. Education and culture absorbed the quantized atom as a symbol of the new scientific age. Textbooks depicted electrons circling nuclei in shells, labeled by numbers and letters. The image was simplified, sometimes misleading, but it conveyed the essence of quantization to generations of students. Popular science embraced the picture of electrons jumping between levels, emitting light as they moved. The atom, once invisible and abstract, was now an icon etched into the imagination of the 20th century. As the full machinery of quantum mechanics emerged in the 1920s, the picture of orbits gave way to probability waves. Schrödinger's equation described electrons not as particles in fixed paths, but as standing waves, spread out in orbitals. Heisenberg's matrix mechanics abandoned visualization altogether, focusing on mathematical relationships between observables. Yet even as these more sophisticated theories displaced the planetary orbits, they preserved the central idea. Electrons could occupy only certain discrete energy states. Bohr's quantization survived, even as the details of his model were replaced. Bohr himself was deeply engaged with these developments. He welcomed the advances of his younger colleagues and sought to integrate them, into a coherent interpretation of quantum theory. His principle of complementarity emerged from this effort, emphasizing that wave and particle descriptions are not contradictory, but mutually necessary perspectives. This philosophical stance grew directly from the recognition, first embodied in his 1913 model, that electrons did not conform to classical categories. They inhabited quantized levels that required new ways of thinking. Looking back, it is striking how the concept of quantized energy levels unified so many disparate threads. It explained the stability of atoms, the patterns of spectra, the periodicity of elements, and the behavior of light-matter interactions. It guided experimentalists in designing new tests, and it offered a framework for technologies that reshaped human society. Few single ideas in science have carried such breadth of influence, extending from the laboratory to the classroom, from philosophy to industry. Even today, the quantized atom remains central to how we teach and understand physics. Students first encounter the idea in simplified diagrams of shells and jumps, often before they are ready to grapple with the full complexity of wave mechanics. This pedagogical role reflects not only convenience, but history. The Bohr atom remains the gateway into the quantum world, a bridge between intuition and abstraction. It is a model that, while outdated in detail, continues to shape the imagination. The endurance of the idea lies in its elegance. Quantized energy levels are at once simple and profound, offering a clear visual metaphor while hinting at deeper mysteries. They invite us to picture electrons climbing ladders of energy, releasing bursts of light as they descend. They remind us that nature is not always continuous, but punctuated by sudden leaps, governed by laws that transcend everyday experience. In these leaps lies the essence of quantum theory, a truth first glimpsed through Bohr's model. As history shows, revolutions in thought often begin with such glimpses. They start as approximations, partial answers that capture essential truths without resolving every detail. The Bohr atom was such an approximation. Its quantized levels were not the final word, but they were the right insight at the right moment, a compass pointing toward the new physics of the 20th century. From that compass grew an entire landscape of discovery, one that continues to expand today. The story of quantized energy levels is ultimately the story of how humanity learned to see the invisible order within matter. It is a story of persistence, creativity, and courage, of scientists willing to abandon old certainties and embrace strange new rules. It is a story that stretches from the dim glow of hydrogen tubes in 19th century laboratories to the bright lasers and microchips of the modern world, and at its center stands Niels Bohr, the pioneer who revealed that the atom's electrons do not wander aimlessly, but dance upon the discrete steps of a quantum ladder, shaping the universe with every leap they make. When historians of science look back at the dawn of the 20th century, they often describe it as a time of uncertainty, a period when the classical picture of nature was unraveling. The certainty that Newton's laws governed the motion of planets and particles alike was giving way to new puzzles that seemed resistant to explanation. At the heart of these puzzles stood the atom, a tiny structure whose secrets refused to yield to classical reasoning. It was into this environment that Niels Bohr stepped, and through his daring ideas he laid the foundation upon which the towering edifice of quantum mechanics would later rise. Bohr's most famous contribution, his atomic model of 1913, did more than explain the spectrum of hydrogen. It introduced the radical notion that the microscopic world followed rules entirely different from those of the macroscopic world. Electrons were confined to quantized energy levels, transitions between them produced discrete photons, and stability arose not from continuous forces but from restrictions imposed by quantum conditions. This was not a refinement of classical physics, but a departure from it, and in that departure lay the seed of a new discipline. By insisting that the atom could only be understood through quantum postulates, Bohr opened the path to what would soon be called quantum mechanics. In the years following 1913, physicists wrestled with the implications of Bohr's proposal. His model worked astonishingly well for hydrogen, but struggled with multi-electron atoms. Critics pointed out its shortcomings, yet they could not ignore the brilliance of its central idea. Each failure spurred new attempts to generalize, to refine, to rebuild, and in this collective effort the outlines of quantum mechanics began to appear. Sommerfeld added elliptical orbits and relativistic corrections. Heisenberg would later abandon orbits altogether, and Schrödinger would describe electrons as waves. All of these later developments drew their inspiration from Bohr's initial leap into quantization. Without his boldness, the community might have remained trapped in the limitations of classical imagery. Bohr also played a decisive role in shaping the intellectual climate of physics. In 1921, he established the Institute for Theoretical Physics in Copenhagen, which quickly became a gathering place for the brightest young minds of the era. There, in a spirit of collaboration and constant debate, quantum mechanics was forged. Students and colleagues like Werner Heisenberg, Wolfgang Pauli, and Lev Landau found in Bohr both a mentor and a challenger. He asked penetrating questions, pressed them to think beyond formulas, and emphasized the importance of interpretation as much as calculation. In this atmosphere, ideas were tested, discarded, and rebuilt until the revolutionary framework of quantum mechanics emerged in the mid-1920s. What distinguished Bohr was not only his technical contributions, but also his philosophical vision. He understood earlier than most that quantum theory demanded new ways of thinking. The principle of complementarity, which he later articulated, grew directly out of this conviction. It held that particles like electrons and photons could be described as waves or as particles, depending on the experimental context, but never both simultaneously. This was not a defect of theory, but a reflection of the nature of reality itself. Such insights transformed quantum mechanics from a set of mathematical tricks into a coherent worldview, one that recognized the limits of classical categories and the necessity of embracing duality. Bohr's foundation for quantum mechanics was therefore both scientific and conceptual. Scientifically, he gave the world the quantized atom, the first working model that explained spectra and stability. Conceptually, he guided the community toward acceptance of discontinuity, probability, and complementarity as fundamental features of the microscopic world. These were not easy truths, and even great physicists like Einstein struggled to accept them. But Bohr's persistence, his clarity, and his steady influence helped solidify the new physics at a time when it might have fractured under doubt and disagreement. By the mid-1920s, the formal mathematical structures of quantum mechanics were in place, thanks to the pioneering work of Heisenberg, Schrödinger, and Dirac. Yet behind their equations lay Bohr's original insight that the atom is quantized, that energy comes in discrete packets, that nature at small scales does not yield to classical continuity. It was Bohr who had first articulated these ideas with conviction, defended them against skepticism, and nurtured the generation of physicists who brought them to full expression. This is why, when we say he laid the foundation for quantum mechanics, we speak not in metaphor, but in historical truth. His vision of the atom was the cornerstone upon which the new physics was built. The consequences of this foundation extend far beyond academic theory. The quantum mechanics that grew from Bohr's pioneering steps became the basis for technologies that define the modern world's semiconductors, lasers, nuclear energy, quantum chemistry, and more recently, quantum computing. Each of these advances can be traced back to the realization that matter behaves according to quantized laws. Without Bohr's early insistence on energy levels and discontinuity, the theoretical framework needed for these technologies might never have emerged, or would have been delayed by decades. His contribution was thus not only intellectual, but also profoundly practical, shaping the course of human history through science and technology. Yet Bohr himself never claimed to have the final answers. He repeatedly stressed the provisional nature of his model, the incompleteness of his ideas, and the need for collaboration. He was as much a philosopher as a physicist, guiding discussions toward deeper meanings and urging caution against dogmatism. In this humility lay his greatest strength, for it created a space in which younger scientists could thrive, experiment, and ultimately surpass him. His foundation was not a rigid structure, but a flexible framework, strong enough to support progress yet open to revision. Today, when physicists teach quantum mechanics, they often begin with Bohr's model of the hydrogen atom. It is not because the model is complete, it is not, but because it represents the first glimpse of the quantum world, the first step into a realm where energy levels are discrete and reality defies classical expectation. It remains the doorway through which generations of students pass, just as it was the doorway through which modern physics emerged. The foundation Bohr laid is still visible, even as the building of quantum mechanics has grown more intricate and vast. In the story of science, few figures have so decisively changed the course of thought as Niels Bohr. By daring to suggest that electrons inhabit quantized energy levels, by nurturing a community that forged a new physics, and by articulating principles that reshaped our conception of reality, he established the groundwork for quantum mechanics. His legacy endures in every experiment, every theory, and every application that springs from the quantum world. The atom, once a riddle, became a window into the deepest truths of nature because Bohr had the vision to see beyond the limits of his time. His foundation remains unshakable, a testament to the power of imagination guided by evidence, and to the courage of a pioneer who revealed that the universe is stranger and far more beautiful than classical reason had ever imagined. When quantum mechanics emerged in the 1920s, it was not only a scientific revolution, but a philosophical upheaval. The equations of Heisenberg and Schrödinger could predict experimental results with extraordinary accuracy, yet their meaning was far from clear. Did electrons truly exist as waves or as particles? Could light be both a stream of photons and a continuous wave? Classical physics demanded a single description, but experiments seemed to insist on a dual nature. It was in this atmosphere of uncertainty that Niels Bohr offered one of his most enduring contributions to human thought, the principle of complementarity. The principle of complementarity arose from Bohr's conviction that the strangeness of quantum phenomena was not a flaw of theory, but a reflection of reality itself. He argued that objects at the quantum scale could not be fully described by any single classical concept. Instead, they required complementary descriptions, each valid in its own context yet mutually exclusive. For example, an electron could be treated as a particle in experiments that measured its localized impacts, and as a wave in experiments that revealed interference patterns. Neither description alone captured the full truth, but together they offered a complete picture. In Bohr's view, this was not a paradox, but a profound lesson about the limits of human understanding. The famous double-slit experiment illustrated his principle vividly. When electrons or photons were fired at a barrier with two slits, they created an interference pattern typical of waves, suggesting that each particle somehow passed through both slits simultaneously. Yet, when detectors were placed to observe which slit the particle passed through, the interference vanished, and the results resembled particles passing through one slit or the other. Wave and particle behaviors could be observed, but never both at the same time. This, Bohr argued, demonstrated complementarity in action. The nature of quantum objects depended not on what they were in themselves, but on how we chose to measure them. Bohr's principle extended beyond physics into philosophy. It challenged the idea that reality could be described by one all-encompassing picture. Instead, reality demanded multiple perspectives, each limited but necessary. This was a radical departure from the reductionist ambition of classical science, which had sought to explain everything through a single framework of laws. Bohr suggested that the truth at the quantum level was richer and subtler, requiring acceptance of ambiguity and duality. For many, this was deeply unsettling, but Bohr embraced it as a natural extension of scientific humility. The debates between Bohr and Einstein over the interpretation of quantum mechanics revolved around this principle. Einstein, uncomfortable with indeterminacy and complementarity, insisted that the theory was incomplete, famously declaring that God does not play dice. Bohr responded that it was not nature playing dice, but human expectation that needed adjustment. He maintained that quantum mechanics was complete within its domain, and that complementarity was the key to understanding its apparent contradictions. Their exchanges, conducted in private conversations and public conferences, remain among the most famous dialogues in the history of science, representing two contrasting visions of reality. Complementarity also shaped the Copenhagen interpretation of quantum mechanics, which became the dominant framework for understanding the theory. According to this interpretation, quantum mechanics does not describe an objective reality independent of measurement. Instead, it describes the outcomes of experiments, with complementarity guiding how those outcomes are understood. The wave function provides probabilities, not certainties, and measurement selects one outcome at the expense of others. Bohr's principle provided the philosophical glue that held this interpretation together, offering a way to reconcile the mathematics with the bewildering behavior of the quantum world. What made complementarity so powerful was its universality. While born from the peculiarities of quantum physics, the principle resonated across disciplines. In biology, psychology, and even the humanities, scholars found in complementarity a metaphor for understanding complex systems that could not be reduced to a single viewpoint. Bohr himself suggested that the principle might apply broadly to human knowledge, reflecting the need for multiple perspectives in capturing the richness of experience. In this sense, his idea transcended physics, becoming a philosophical lens through which to view the relationship between observer and reality. Yet Bohr was not merely a philosopher. He remained a scientist deeply committed to the experimental grounding of his ideas. He emphasized that complementarity was not speculation but necessity, demanded by the evidence of quantum experiments. Without it, the dual behavior of particles and waves remained irreconcilable. With it, the contradictions dissolved into a higher understanding, where opposites became partners in truth rather than enemies in conflict. The influence of complementarity continues to this day. In quantum information theory, the dual nature of states underlies the logic of quantum computing and cryptography. In debates about the interpretation of quantum mechanics, the principle remains a touchstone, whether embraced, challenged, or reimagined. Its endurance testifies to the depth of Bohr's insight, an idea born not from abstract speculation, but from a careful confrontation with the stubborn realities of the quantum world. Bohr introduced complementarity not as a final word but as a guide, a way of navigating the unfamiliar terrain of quantum physics. It asked scientists to accept the limits of human concepts, to embrace the coexistence of multiple perspectives, and to resist the temptation of absolute certainty. This intellectual humility, coupled with bold imagination, was Bohr's hallmark. Through complementarity, he gave physics not just a principle but a philosophy, one that continues to shape the dialogue between science and reality. In the end, complementarity reflects the spirit of Bohr himself, calm, thoughtful, and willing to embrace complexity rather than simplify it away. It remains one of the great intellectual landmarks of the 20th century, a principle that reshaped physics and invited humanity to rethink its relationship with the universe. Through this insight, Niels Bohr showed that the quest for knowledge is not always about finding singular answers, but about learning to see from multiple angles, accepting that truth may require complementing, not replacing perspectives. This was his gift to science and to philosophy, a legacy that endures wherever the mysteries of the quantum world are studied and wherever the limits of human understanding are acknowledged. When we reflect on the legacy of Niels Bohr, we often think of his atomic model, his principle of complementarity, and his debates with Einstein. Yet an equally important part of his influence lies not in equations or theories, but in the way he shaped generations of scientists through collaboration, mentorship, and his vision of science as a shared human endeavor. Bohr was not only a pioneer of quantum theory, but also an architect of a new scientific culture, one built upon dialogue, openness, and the global exchange of ideas. Bohr's Copenhagen Institute for Theoretical Physics, founded in 1921, became the living heart of this vision. More than a research center, it was a gathering place where the brightest minds of physics could meet, learn, and challenge one another. Young physicists from around the world flocked to Copenhagen to work under Bohr's guidance. They were not treated as mere assistants, but as partners in discovery, encouraged to question boldly and think freely. In an era when science was often hierarchical and guarded, Bohr's institute was radical in its openness. He cultivated an atmosphere where students and visiting scholars alike could debate the deepest questions of physics, often around his famous blackboard or in informal discussions at his home. It was at Copenhagen that many of the great names of 20th-century physics, Werner Heisenberg, Wolfgang Pauli, Lev Landau, George Gamow, and others, came into their own. Heisenberg, who developed matrix mechanics and the uncertainty principle, credited Bohr's influence as crucial to his intellectual development. Pauli, known for his exclusion principle, found in Bohr not only a mentor but a sparring partner whose probing questions sharpened his own thinking. For these young pioneers, Bohr was more than a teacher, he was a guiding presence, pushing them to see the deeper implications of their work and to appreciate the unity of physics as a whole. The discussions in Copenhagen were not merely technical, they often extended into philosophy, art, and even politics. Bohr believed that science was inseparable from broader human culture. He saw the mysteries of the quantum atom as connected to questions of knowledge, language, and society. This holistic view attracted thinkers from many fields, making his institute not only a physics laboratory but a cultural hub. In this way, Bohr expanded the meaning of scientific education, training not just specialists but thinkers who could bridge disciplines. Bohr's role as a collaborator extended far beyond Denmark. He traveled widely, giving lectures and engaging in dialogues with scientists across Europe, America, and later the Soviet Union. His calm and thoughtful style made him a respected figure in international circles, even among those who disagreed with his interpretations of quantum mechanics. During the interwar years, when Europe was torn by political divisions, Bohr's institute became a rare place of unity, where nationality mattered less than curiosity and dedication to science. He welcomed scientists of all backgrounds, offering refuge to many during the rise of fascism in the 1930s. When Jewish physicists were forced to leave Germany, Bohr extended invitations and support, helping them find new opportunities abroad. In doing so, he not only protected individuals, but preserved the continuity of scientific knowledge at a time of great disruption. After World War II, Bohr's vision of collaboration took on even greater significance. The development of nuclear weapons had shown both the power and the danger of scientific discovery. Bohr, who had contributed to nuclear research during the war, emerged as a voice for openness and international cooperation. He argued that science could not thrive in secrecy and isolation. Knowledge, in his view, was a common human heritage that needed to be shared across borders. He met with leaders and advocated for the peaceful use of atomic energy, believing that global communication was essential to preventing destructive competition. His calls for an open world became a central theme of his later life, extending the spirit of his Copenhagen Institute to the international stage. Through his writings and speeches, Bohr emphasized that education was not just the transfer of facts but the cultivation of attitudes, curiosity, humility, and a willingness to embrace uncertainty. He reminded students and colleagues alike that science was not about claiming absolute truths, but about refining our understanding of nature through dialogue and experiment. This philosophy shaped the way physics was taught and practiced, embedding in future generations the collaborative ethos that defined 20th-century science. The legacy of Bohr's educational role can be seen in the extraordinary impact of his students and collaborators. Many went on to win Nobel Prizes, to build new branches of physics, and to establish their own schools of thought. Each carried forward something of Bohr's spirit: the insistence on clarity of concepts, the respect for multiple perspectives, and the commitment to collaboration. Through them, Bohr's influence reached far beyond what any one individual could achieve, spreading across continents and decades. Bohr's vision was not confined to elite institutions. He believed deeply in the democratization of knowledge. He supported efforts to bring science into public life, to make its discoveries accessible to ordinary people, and to connect it with the ethical responsibilities of society. In his speeches, he often stressed that scientific progress must go hand in hand with human progress. To educate scientists was not only to train technical experts, but to prepare responsible citizens of the world. In many ways, Bohr embodied the ideal of a scientific statesman. His authority did not rest on political power or wealth, but on trust, earned through decades of intellectual honesty and generosity. People turned to him not only for insight into physics, but for wisdom on how science could serve humanity. In an age when the pace of discovery threatened to outrun society's ability to adapt, Bohr's voice was a steady reminder that education and collaboration were the keys to balance. The image of Bohr as a teacher remains one of the most enduring. Those who studied under him recalled his habit of pausing for long silences, as though weighing the meaning of every word before speaking. He would often respond to a question with another question, guiding the student to discover the answer through their own reasoning. This method, at once gentle and demanding, reflected his belief that true education was not the giving of answers, but the awakening of thought. His institute, his lectures, and his conversations all embodied this approach, leaving behind not just scientific results, but a way of thinking that continues to inspire. Niels Bohr's role in education and collaboration reveals a dimension of science often overlooked: the human dimension. The great discoveries of quantum theory did not emerge from solitary genius alone, but from a community of minds working together, challenging, and learning from one another. Bohr understood this better than most. He saw himself not as the sole author of knowledge, but as a participant in a shared endeavor that crossed generations and borders. By building spaces where dialogue could flourish, by mentoring with patience and depth, and by advocating for openness in science, he ensured that the pursuit of knowledge would remain a collective journey. In the story of physics, Niels Bohr's equations may be written in textbooks, but his spirit lives on in the way science is practiced, in international collaborations, in the mentorship of young researchers, and in the recognition that the search for truth is best undertaken together. His contribution to collaboration and education worldwide is a reminder that the greatest legacies are not only discoveries, but the communities and values that sustain them. In the year 1922, the world of science recognized a man whose ideas had already begun to transform humanity's understanding of the universe. Niels Bohr, the Danish physicist who reimagined the atom and dared to see beyond the limits of classical physics, was awarded the Nobel Prize in Physics for his contributions to the structure of atoms and the radiation they emit. It was not simply a medal or a moment of ceremony, it was the world's acknowledgement that a new chapter in science had begun. To appreciate the weight of this recognition, one must understand the context of the time. Physics had entered a period of crisis in the early 20th century. Classical theories, once thought unshakable, were failing to explain phenomena at the smallest scales of nature. Spectroscopy revealed strange patterns of light emitted by atoms, patterns that no existing theory could decode. The stability of atoms themselves was a mystery, for according to classical electrodynamics, orbiting electrons should radiate away their energy and spiral into the nucleus in a fraction of a second. The universe as observed did not match the predictions of the science inherited from Newton and Maxwell. It was into this confusion that Bohr stepped with his revolutionary atomic model. Bohr's model, proposed in 1913, introduced the daring idea that electrons move in quantized orbits around the nucleus, allowed only certain energy levels, and could jump between these levels by absorbing or emitting discrete packets of energy called quanta. It was a bold fusion of Rutherford's nuclear atom and Planck's quantum hypothesis, one that seemed almost paradoxical but matched experiment with uncanny accuracy. For the first time, the strange regularities of atomic spectra could be explained, and the stability of atoms could be understood. The world of physics suddenly had a guiding light. By 1922, the impact of Bohr's model was undeniable. It had inspired new experiments, reshaped the teaching of physics, and given rise to a generation of young scientists eager to probe deeper into the quantum world. The Nobel Committee recognized not just a single discovery, but the foundation of an entirely new field. Awarding Bohr the Nobel Prize was, in many ways, awarding the birth of modern atomic physics. The ceremony in Stockholm was both a personal milestone and a historical event. Bohr, modest by nature and often uncomfortable with fame, accepted the award not as a solitary triumph, but as a testament to the collective endeavor of science. He acknowledged the contributions of his predecessors, Rutherford, who had revealed the nucleus, and Planck, who had introduced the quantum. He also emphasized the collaborative spirit of research, noting that science progresses not through isolated genius, but through a web of shared insights, experiments, and debates. His humility only deepened the respect with which the scientific community regarded him. The Nobel Prize brought Bohr into the public spotlight, transforming him from a respected physicist into an international figure. Newspapers carried his name, and his ideas entered popular discussions about the future of science. For many, the atomic model became a symbol of the new age, a glimpse into the hidden architecture of reality. Bohr himself remained focused on research and teaching, but he understood that the recognition carried responsibilities. The Nobel Prize gave him not only honor, but also a platform to promote his vision of science as a universal and collaborative pursuit. The timing of the award was significant. The early 1920s were a period of rebuilding after the devastation of World War I. Science, like much of society, was seeking new directions and fresh unity. By honoring Bohr, the Nobel Committee highlighted the potential of intellectual discovery to transcend national boundaries and to remind humanity of its shared quest for knowledge. Bohr's Institute in Copenhagen was already becoming a hub for international collaboration, and the Nobel Prize further elevated its stature, attracting even more young physicists from around the world. It was a recognition not only of Bohr's past work, but of the promise of the environment he was creating. The Nobel Prize also validated the strange and unsettling ideas of quantum theory, which at that time were still met with skepticism in many circles. By awarding Bohr, the committee effectively acknowledged that physics was entering a new era where classical intuitions could no longer dictate truth. This gave courage to those exploring uncharted theoretical territory, Heisenberg, Schrödinger, Dirac, and others who would soon expand quantum mechanics into a full formalism. Without Bohr's Nobel Prize, the acceptance of these new ideas might have faced even greater resistance. In the years that followed, Bohr used his Nobel status to champion both scientific and human causes. He welcomed students and colleagues from across the world to Copenhagen, treating the prize not as a personal victory, but as a resource for fostering collaboration. He believed that the honor bestowed upon him was inseparable from his responsibility to nurture the next generation. Many of those who studied under him would themselves go on to win Nobel Prizes, a testament to how Bohr's recognition rippled outward, multiplying its impact. The symbolism of the Nobel Prize in 1922 extended beyond physics. It marked a moment when humanity looked deeper into the atom and realized that within its tiny structure lay the keys to immense power and mystery. Decades later, that power would be harnessed in ways both creative and destructive, from nuclear energy to atomic weapons. Bohr foresaw these possibilities and constantly reminded the world of the ethical responsibilities tied to knowledge. In this sense, the Nobel Prize was not merely a celebration of discovery, but the beginning of a conversation about how such discoveries should serve humanity. Even after receiving the award, Bohr remained characteristically humble. He often remarked that his model was only an approximation, a first step toward a deeper truth that future generations would uncover. Indeed, within a decade, quantum mechanics would surpass the Bohr model, replacing orbits with probability clouds and wave functions. Yet the Nobel Prize was never about the finality of his theory. It was about the courage to propose a new vision, the insight to explain what had been unexplainable, and the ability to open doors to entirely new ways of thinking. Today, when historians recount the history of science, Bohr's Nobel Prize in 1922 is seen as a turning point, a recognition that the old order of physics had given way to the quantum revolution. It signified the acceptance of uncertainty, the embrace of new logic, and the beginning of technologies that would shape the modern world. The image of Bohr standing in Stockholm, a quiet and thoughtful man receiving the world's highest scientific honor, represents not just an individual achievement, but a milestone in human understanding. Through that moment, Niels Bohr became not only a Nobel laureate, but a symbol of the power of imagination guided by evidence. His prize was a beacon to scientists everywhere that even the most counterintuitive ideas, if grounded in experiment and reason, could change the very framework of reality. It was a reminder that science is a journey of bold steps, often taken in uncertainty but leading to horizons of unimaginable possibility. The Nobel Prize of 1922 enshrined Bohr's place in history, but more importantly, it enshrined the spirit of discovery that he embodied, a spirit that continues to inspire all who seek to understand the universe.